Introduction. Today, Ravi is alone at home. He's doing his study. Suddenly, the doorbell rings. He opens the door and greets with a smile on seeing his father. Ravi asked his father how the doorbell works. His father replied to him that the doorbell works on the principle of solenoid. Solenoid is a circular current-carrying coil. When the current passes through it, then it behaves like a magnet. Students, you also must be curious like Ravi to know more about this. So today, we'll explore the moving charges and magnetism. Objectives. At the end of this lesson, we'll be able to define Ampere's Circuital law, describe solenoid and toroid, evaluate force between two parallel current-carrying conductors, calculate torque on a rectangular current loop, calculate magnetic dipole moment of a revolving electron, explain moving coil galvanometer, convert galvanometer into ammeter and voltmeter. Ampere's Circuital law. Ampere's Circuital law relates the integrated magnetic field around a closed loop to the electric current passing through the loop. It states that the line integral of the magnetic field B along any closed path is equal to mu naught times the net current I passing through the area bounded by the path. It is mathematically represented by close integral of B dot dl is equal to mu naught I. It provides a simple method for calculating the magnetic fields of current configurations which has high symmetry. Magnetic field due to an infinitely long current carrying wire. We have to calculate the magnetic field at a distance r from the wire. By symmetry, the magnitude of the field B is the same at all points of the loop, and its direction at a point is along the tangent to the circle at the point. The line integral of the magnetic field B around the circular loop is given by product B and 2 pi r. Also, by Ampere's Circuital law, closed integral of B dot dl is equal to mu naught I. From above two equations, we get the result B is equal to mu naught I divided by 2 pi r. Example. Let's take an example on magnetic field due to a current-carrying conductor. A long straight conductor carries a current of 120 ampere. At what distance from the conductor is the magnetic field caused by the current equal to 0.8 into 10 raised to the power minus 4 Tesla? Let's see the solution. Here, the given values are I is equal to 120 ampere, B is equal to 0.8 into 10 raised to the power minus 4 Tesla. Mu naught is equal to 4 pi into 10 raised to the power minus 7 SI units. We know that B is equal to mu naught I upon 2 pi A. By putting the values in the equation, we get the values of A is equal to 0.3 meters. Hence, at 0.3 meters from the conductor, the magnetic field caused by the current equal to 0.8 into 10 raised to the power minus 4 Tesla. Solenoid. A solenoid is a current-carrying wire wound around the surface of a right circular cylinder. To find the magnetic field inside a long solenoid, we consider a rectangular loop ABCD. The segment AB of length L is parallel to the axis of the solenoid. The integral for the rectangular path ABCD consists of 4 integrals, one for each segment. Closed integral of B dot dl is equal to integration from A to B of B dot dl plus integration from B to C of B dot dl plus integration from C to D of B dot dl plus integration from D to A of B dot dl. It gives closed integral of B dot dl is equal to integration from A to B of B dot dl, which is equal to BL. According to Ampere's Circuital law, closed integral of B dot dl is equal to mu naught NIL, where N is the number of turns per unit length. From above two equations, we get the result B is equal to mu naught Ni. Toroid. A toroid is a current-carrying wire wound around a donut-shaped core. An ideal toroid consists of closely spaced current turns that the magnetic field is completely confined to the interior of the donut. From symmetry, the magnitude of the magnetic field B is the same at all points on the circle of radius r and is directed tangentially to the circle at any point. Thus, the line integral of the magnetic field B around the circular loop is given by the product of B and 2 pi r. According to Ampere's Circuital law, closed integral of B dot dl is equal to mu naught Ni, where N is the total number of turns. From above two equations, we get the result B is equal to mu naught Ni divided by 2 pi r. Field due to parallel currents. It represents the combined magnetic field due to two parallel conductors carrying current in the same direction. The pattern of the magnetic field indicates attraction between the conductors. It represents the combined magnetic field due to two parallel conductors carrying currents in opposite direction. The pattern of the magnetic field indicates repulsion between conductors. Force between two parallel current-carrying conductors. Let us consider two long, straight, parallel wires separated by distance r and carrying currents I1 and I2 in opposite directions. Wire 1 carries a current I1, sets up a magnetic field B1 at all points along the wire 2. This magnetic field is directed perpendicularly upward to wire 2 and has the magnitude equal to mu naught I1 divided by 2 pi r. The magnetic force magnitude on wire 2 due to wire 1 is given by mu naught I1 I2 L divided by 2 pi r. An equal and opposite force, F12, acts on wire 1 due to the magnetic field produced by wire 2. F21 is equal to minus F12. Consequently, the forces between the wires are repulsive. In case the currents are in the same direction in the two wires, the forces between the wires are reversed and hence attractive. One ampere. We know that F is equal to mu naught upon 2 pi multiplied by I1 I2 upon R, when I1 is equal to I2 is equal to 1 ampere and R is equal to 1 meter. Then the value of F is equal to 2 into 10 raised to the power minus 7 Newton per meter. Therefore, 1 ampere is that current which, if passed in each of the two parallel conductors of infinite length and 1 meter apart in vacuum, causes each conductor to experience a force of 2 into 10 raised to the power minus 7 Newton per meter of length of conductor. Torque on a rectangular current loop. We consider a current-carrying rectangular loop PQRS of sides A and B placed in an external uniform magnetic field B. The normal to the plane of the loop makes an angle theta with B. When a current I flows through the loop, each straight segment experiences a force. The forces F1 and F3 are equal in magnitude, opposite in direction and collinear, so the net force and torque due to these forces are zero. The forces F2 and F4 are also equal in magnitude and opposite in direction, so they produce no net force. However, since the two forces are not collinear, they exert a torque on the loop, with magnitude equal to product of force and lever arm, which is equal to IAB sin theta, where A is the area of loop. The above equation can be written as tau is equal to mb sin theta, where m is the magnitude of magnetic dipole moment. Tau is equal to the cross product of m and b. Current loop as a magnetic dipole. The magnetic dipole moment m of a circular current loop carrying a current I and of area A is given by m is equal to product of I and A r cap. The direction of m is given by the right-hand thumb rule. Right-hand thumb rule states that if the current is directed along the four curved fingers of the right hand, then the extended thumb points in the direction of the magnetic dipole moment. Magnetic dipole moment of a revolving electron. The magnetic moment arising from the orbital motion of the electron is given by EVR by 2. The direction of this magnetic moment is perpendicularly into the plane. If ME is the mass of the electron, the revolving electron also possesses an angular momentum with magnitude. I is equal to MEVR. From above two equations, we get the result mu L is equal to minus E upon 2ME multiplied by L. The negative sign indicates that the two vectors are in opposite directions. Gyromagnetic ratio. Mu L upon L is equal to E upon 2ME. Its value is 8.8 into 10 raised to the power 10 coulomb per kilogram for an electron. Bohr magneton. Mu B is equal to EH upon 4 pi ME. Its value constant and equals to 9.27 into 10 raised to the power minus 24 atm square. Moving coil galvanometer. The galvanometer is a device used in the construction of both ammeter and voltmeter. It works on the principle that a current-carrying coil suspended in a uniform magnetic field experiences a torque which balances the restoring torque produced by the twisting of the suspension spring. The galvanometer consists of a coil of fine wire of many turns wound on a cylindrical soft iron core hung from a spring and carrying the current I to be measured. The pole pieces are cylindrical in shape so that the coil rotates in a field that is everywhere radial. This radial force ensures that the deflecting torque is directly proportional to the current and is always constant. Parameters of moving coil galvanometer. The steady deflection for a galvanometer is given by NBA upon K multiplied by I, where N is number of turns in the coil, A is the area of coil, and K is the torsional constant of the spring. The current sensitivity of a galvanometer is defined as the deflection produced in the galvanometer when a unit current flows through it. Current sensitivity is equal to phi upon I, which is equal to NBA upon K. The voltage sensitivity of a galvanometer is defined as the deflection produced in the galvanometer when a unit voltage is applied across it. Voltage sensitivity is equal to phi upon V, which is equal to NBAI upon KV. Conversion of galvanometer into ammeter. To measure the current in a circuit, an ammeter must be inserted in series in the circuit so that the current to be measured passes through it. The range of the galvanometer can be extended, and at the same time, the equivalent resistance can be reduced by connecting a low resistor S in parallel with the galvanometer. The resistor S is called the shunt resistor. The galvanometer and parallel resistor combination is called an ammeter. V is equal to product of Ig and G, or V is equal to product of Is and S. On equating both above equations, we get the value of S is equal to Ig upon Is into G. We know that I is equal to Ig plus Is. Hence, the value of S is equal to Ig upon I minus Ig into G. With this value of S, the ammeter is able to measure a large current up to I, and it has a low resistance. Conversion of galvanometer into voltmeter. To measure potential difference across a given section of a circuit, the voltmeter must be connected in parallel with that section of the circuit. The range can be extended, and at the same time, the equivalent resistance can be increased by connecting a resistance in series with the galvanometer. The galvanometer and series resistor combination is called a voltmeter. Applying Ohm's law to the circuit, we get V upon Rs plus G within parentheses is equal to Ig. It can be written as Rs is equal to V upon Ig minus G. Rs must be put in series with the galvanometer in order that it may be used as a voltmeter. The voltmeter has a high resistance Rs plus G within parentheses. Did you know? A solenoid switch is used as a control device. It utilizes electromagnetic energy so as to convert the input electrical energy to mechanical energy. Modern uses for the galvanometer mechanism are in positioning and control systems. Solenoid is used as an interlock device for integration into automatic gearbox drive selectors, petrol cap locking, vibration engine mountings, and security systems. Summary. Let us summarize what we have learned. Ampere's circuital law relates the integrated magnetic field around a closed loop to the electric current passing through the loop. A solenoid is a current-carrying wire wound around the surface of a right circular cylinder. A toroid is a current-carrying wire wound around a donut-shaped core. When the currents are in the same direction in the two conducting wires, the forces between the wires are attractive. 1 ampere is that current which, if passed in each of the two parallel conductors of infinite length and 1 meter apart in vacuum, cause each conductor to experience a force of 2 into 10 raised to the power minus 7 Newton per meter of length of conductor. Right-hand thumb rule states that if the current is directed along the 4 curved fingers of the right hand, then the extended thumb points in the direction of the magnetic dipole moment. Moving coil galvanometer works on the principle that a current-carrying coil suspended in a uniform magnetic field experiences a torque which balances the restoring torque produced by the twisting of the suspension spring. The current sensitivity of a galvanometer is defined as the deflection produced in the galvanometer when a unit current flows through it. The galvanometer and series resistor combination is called a voltmeter.